So here we go. Your notes today are actually examples from the worksheet. I'm going to do a couple of the problems, and you guys do a couple of the problems. And we're drawing slope fields. We're working with slope fields today. And remember, slope field is a way of representing a differential equation. Usually slope fields are reserved for ones that you can't find the antiderivative of. They're a necessity. You have to do it because you can't do it algebraically, solve the differential equation algebraically. But this one's obviously okay to do. So here's the idea. First one, draw the slope field. So what you're going to do is, remember the slope field is a little dash whose slope of that little dash line is equal to the differential equation at that point. So for example, if I want to put my little dash on the point 1, 1, what I have to do is I have to evaluate the differential equation at the point 1, 1. That's how you tell that that's the notation for evaluating at a particular place. So I plug in 1 for x and 1 for y equals 2. This was actually kind of easy that way. Some a little more difficult, some a little easier. So the slope of my line at that point is the slope of 2, which is about like that. Actually, that's way too big. It's about like that. And your slope field is just doing that repeatedly. Now, if you got a computer that'll do it for you, it looks really pretty and easy because they can just compute them, no problem. You will have to do them by hand. So, pick another point. I'm going to do the point 2, 1. So dy dx at the point 2, 1 is 2 plus 1, which is 3. So I have a slope of 3. Now, I could, if I really, really wanted to, and I know some of you are OCD, right? What during my generation would call anal.
Oh, God.
Anal retentive OCD. Yeah, they just came up with a name that doesn't sound as bad. And you take your ruler and you set it up. Okay, that's a slope of 3, and so I draw that. But realistically, all you got to do is just make sure it's a little steeper than the one before it. Okay? So if I keep doing this, let's say I'm going to go over here and do this point here, the point -1, 1. So dy dx at -1, 1 is -1 plus 1, or 0, which means I'd have here a horizontal line. Now, for some slope fields, computing each dot is very long and tedious because you can't just look for a pattern. But if I look at this one, I can kind of shortcut this one a little bit. First question I have for you, or first observation, is there are no y's in my differential equation. My differential equation only varies with x, which means that all the vertical values are all exactly the same, because it doesn't matter what y is. Changing my value of y doesn't change the value of my differential equation, only changing my x values. Every single coordinate where x is -1, plug in -1 for x, I get 0. It doesn't matter what the y is. Every one of these has a little horizontal line. Because if I plug in -1, I get what? I get 0.
Wait, why do you not have to worry about the y?
Because do I have any y's in my equation? I don't have any y's in my equation. Y doesn't matter. If I had a y and an x in there, then I'd have to worry about both. And I'd probably have to compute every single one of them. By the same token, if I have a differential equation that doesn't have any x's in it, all I have to do about y's, and all the horizontal lines all the way across will be the same. So I know that those are all the same. So these all have a slope of 2 down here. These all have a slope of 3, which is a little steeper. These ones all have a slope of 4, which will be a little steeper. These ones will have a slope of 1 because x is 0 on every one of these points, which means I have a slope of 1. And on this side here, I have a slope of -1 at every one of these because when x is -2, -2 plus 1 is -1. These points here, -3 plus -3 plus 1, I have a slope of -2 for every one of these. And there's my slope field. Sometimes you got to sit and figure out every single point. Sometimes you don't. Yes?
What is representing you yet?
Okay, this is representing the solutions, all possible solutions to my differential equation. Now, if I take the antiderivative of x plus 1, what do I get? I get 1/2 x squared plus x, right? Plus c. The antiderivative of this, y would be, y would equal 1/2 x squared plus x plus c. If you look at this, what do you see here? You see a parabola, right? Which is what I have here. So it makes sense. This gives me the family of all the parabolas. Now, if I want to find a particular solution, I can plug in the x and the y and find the c. But graphically speaking, let's say I want to go through the point, I want to go through the origin, have it pass through the origin, which c would be 0, right? The origin c would be 0. What would the solution look like here? Well, I start here, and I just kind of follow what's going with my function, and there's the parabola that would go past through the origin. Is it perfect? No. You do it on the computer, which is really pretty. Like I said, Graphmatica will do it for you. I love it on Graphmatica. You have an Apple product, an iPhone, or an iPad. I have it on my iPad, but I have it on the computer here. You can put it on a PC. Any Apple product or a PC. Does not work on Android yet. Okay, your turn. Plot the slope field. No, let's get, yeah. You'll go back and do 2 on your own. I want you to do 3 now. Don't worry. Okay. So it's x plus y. There's patterns to this one as well, but they're a little harder to see. But basically, all you're doing on this one is every xy coordinate, you just add the 2 numbers together. That's the slope of your line. So at 0, 0, my slope would be 0 at the origin. Okay. I would have other places that are also 0, where the x and y coordinate are opposite of each other. Where x is 1, y is -1. Where x is 2 and y is -2. Where x is -1 and y is 1, and so on. Kind of stop and think about it a little bit. Okay? And then I can just start filling in the blanks and start doing it. This is a relatively easy one. On the vertical one, the x-axis, or sorry, on the x-axis, all your y's are 0s, so it's just the value of your x coordinate along the x-axis. So at 1, I have a slope of 1. At 2, I have a slope of 2. At 3, I have a slope of 3. I have -1, -2, -3. If I go to the x-axis, the same thing is true for my y-coordinates. Y is 1, I have a slope of 1. Y is 2, I have a slope of 2. Y is -1. I have a slope of -1. I have a slope of -2. The rest of the points, you got to kind of think about a little bit as you're going along. 1 plus 1 is 2. 1 plus 2 is 3. And then 4. 2 plus 1 is 3. And then and then 4, and then 5. Let's see. Bless you. 2 plus negative 1 is 1. And again. And then I have, so I got 1, and this one's going to be higher by 1. So if you kind of think about it, you do have a pattern here. Negative 1 plus negative 2 is negative 1. What's happening? The slope increases by 1 each time I go to the right, or decreases by 1 each time I go to the left along a horizontal line. Same thing happens along the vertical. So this is going to be a positive 1 here. This is going to be a negative 1 here. It's going to be a negative 1 and negative 2. Negative 1, negative 2, negative 3, negative 4. Negative 1, negative 2, negative 3, negative 4, negative 5. Okay. This is not a parabola. This is not a parabola. This doesn't, it kind of looks a little bit like parabola, but it's not quite a parabola. If you pick a point, let's say I'm going to go through the point 1, 1. It comes down and follows and goes through here, but then it kind of becomes asymptotic to that and then grows up. Okay. If you have a series of ones that are all the same going diagonally, and that's the only place I have that, is every single one of these going across here diagonally are all negative 1, I end up having an asymptote at that point. I have a angled asymptote, not a vertical or horizontal. That's what that looks like when you put in a particular point. Okay. We will be solving that algebraically. Actually, we won't. We can't do that one. We don't have the skills. Slope fields are it. Now, this is where it gets a little interesting. Match each slope field with the equation that the slope field could represent. Wow. Match this slope field to the equation. Okay, now I only have A and B for my pictures up here. You have more, which will match up all of them. They will all be used at some point. Now, there's a couple of ways to think about this. Okay. If I take the derivative, remember, that slope field represents the derivative of these functions. So, what's the derivative of 1? 0. So, everywhere would be 0. Everywhere would be 1 on this one. Everywhere would be 2 times the x value on this one. Okay. Do I have any that look like a parabola up here? So it's not going to be a parabola. It's not going to be a straight line. I don't have any straight lines. I know these 3 are not going to work. Here's a few things you do. Are any of them repeated vertically? Do any of those have where every vertical one is exactly the same? Yeah, actually both of them. So that means I'm not going to have a y as part of my derivative. Great, no problem. That makes that good. Then I start going, okay, what does 1 look like? B is actually, I think, easier than A is. A is not too bad, but B is not too bad either. If I look at B, I have a choice. What does that look like? If I picked out a point on here, say here, and I sketched it out, what does that look like? What does that look like? Looks like a sine curve. It is not a cubic. It is not a square. What does it look like? It looks like a sine. So that's either a sine or a cosine. Now the problem with sine or cosine is they're essentially the same thing. The only difference is at the origin. The sine passes through the origin diagonally. Cosine does not. The cosine of 0, the sine of 0. This one would be cosine because it doesn't cross diagonally here. It doesn't come through diagonally. It'd have to go through like that to be the original one to be a sine function. Does that make sense? This one's a little more complicated. But I got a really good idea which one. What's the value of the slope at 0? There isn't one. I do actually have them. You just can't see them because the way this is, by the way, a calculator screen. This is a screen from the TI that has been cut and pasted in. If you ever see one that looks like this, is exactly what the Slopefields on the TI is. Okay. Only they have a green background. What? You can grab Slopefields on the TI.
You're going to show us how?
No. Because I have no idea. I know you can't. And here's the other thing. You will not have a Slopefield question on the calculator portion of the test. Because they write the test, it doesn't matter which type of calculator you have, it will not help you over another type. And because not all graphing calculators do Slopefields, they will not have that as a calculator question. Any Slopefield questions will be on non-calculator portions of the test. Okay. And they have two types of Slopefield questions. Either you're given a graph and find the, you're given it's either multiple choice and you have the graph and the equations, or you have the equation and then which graph matches it, or you have to do it by hand. So this one's undefined. Which one of these functions is undefined at x equals 0? This one's undefined at x equals 0. So is that. The natural log of 0 is undefined. So now you got to figure out and decide which one works. Which one works? Which one is it? Okay. And see which one matches up to best. Frankly, it could be either. What I would do is use the other ones to help me figure it out. Okay. Although the natural log graph does not increase like this, what does the natural log graph do? Because remember, this is e to the x. What does a natural log graph do? Natural log looks like that. That is not a natural log graph. Okay, if you follow the Slopefields. If you follow this, what do you get? This one would be that. I like this worksheet because it not only does can you tell the difference, but it helps you reinforce understanding and recognizing graphs of functions. What do they look like? What does the original one look like? What does x squared, 1 over x squared look like compared to what does the natural log of x look like? And then you should have an idea what those graphs look like. Now they're mixed, x's and y's. See if you can figure out which ones are which. So I'll look at the first one. And I do not have a horizontal pattern for every single value. I do not have a vertical pattern for every single value. So this is not x only or y only. This is x's and y's. So I got to kind of figure out what's going on. I have choices to work from. There's only 2 equations that combine x's and y's. And if I look at the slope field, you'll notice that every time the x and y coordinate are equal, I have a slope of -1. Every time the x and y are opposite each other, I have a slope of +1. So on the diagonals, I have a slope of -1. I have a slope of +1. Wherever they're the same, I take x divided by y. When they're the same value, I get -1. When they're the same value, I get -1. When they're opposite values, when x and y are opposite values, I divide, I get +1. Opposite values divided, Opposite side of that, 18. That's what this one is. And what is the antiderivative of that going to be? What shape do I have here? I got a circle. And if you take the derivative of a circle using implicit differentiation, that's what you get. We will learn how to solve them. So I look at the next one. And I go, okay, does it have horizontal or vertical or both? You know, do I have a pattern? It looks like I kind of have every pattern the same vertically. Every single line vertically, every single slope vertically is the same, which means it depends upon x, not upon y. When x is a certain value, I get certain ones. So here, when x is -2, I get 0. Next thing is, every time x is -2, I get 0. Which one of these, when I put in -2 for x, do I get 0 every single time? This one. That's the kind of thing you can do when you're answering a problem trying to match it up. Trying to come up with the actual equation from it, you can't really do that, but you can match them together. And that's what you would be asked to do. So this one here would be 15. And this line right here tells me exactly what's going on. I can figure it out from that one. They're all exactly the same. I have a slope of 0. Every time x is -2, I have a slope of 0. If I plug -2 into which one of those do I get to 0? And only 0 every single time, irregardless of what my y coordinate is. That's how that one works. Okay? Questions?